What we've done so far has been theoretical, so today I'd like to talk a little bit more about the real atmosphere. But before we do, I should say that in the last couple of modules, I was trying to project a nice, quiet, dignified air, but my wife tells me that I overshot calm and went straight into boring. So this week, for your entertainment, as always, I'll try to remember to pretend that I'm in class and maybe get a little more worked up. We'll see, I might not pull it off. Anyway, air pressure is the total weight of the atmosphere above a certain point. It essentially tells you how much of the atmosphere is above you. Air pressure at sea level is about 1,000 millibars, and it drops to 200 millibars by the time you get to the top of the troposphere, about 10 to 15 kilometers above the surface. That means that 80% of the atmospheric gases are found in this lowest level of the atmosphere. As we mentioned last time, these gases are mostly nitrogen and oxygen, but some gases, like water vapor, are found mostly near the surface. Ozone, on the other hand, is found higher up in the stratosphere because that's where incoming UV light is strong enough to form it. Atmospheric layers are defined by temperature gradients. In the troposphere, the temperature declines as you go up, which is why mountains have snow on them. The temperature declines with altitude because the troposphere is mostly heated from below as the surface absorbs incoming solar radiation. It also declines because as warm air rises, there's less air above it pushing down, so the pressure goes down, so the air expands, and the expanding gases cool down. So the air cools down as it rises in the atmosphere and warms up as it sinks. One really important result of the temperature decline with height in the troposphere is that the troposphere can be unstable. Because warm air is lighter than cold air, all else equal, the air is usually colder above than below. It doesn't take as much to get warm air to rise in the troposphere as long as it cools down more slowly while it rises than the air around it. If it does so, it's going to keep rising, and that's how thunderstorms get started. Even if the air isn't unstable in this way, the temperature gradient makes it much easier for air to move around in the troposphere, and so you get all the interesting weather that we see here on the surface. On the other hand, temperature rises with height in the stratosphere. That's what defines the stratosphere. That's because the stratosphere absorbs a fair amount of UV light in the ozone layer, and absorbing that energy causes it to heat up. So the stratosphere is warmed from above, unlike the troposphere. An interesting result is that the stratosphere is very stable. If warm air starts to rise, it'll expand and cool, but it'll be rising into increasingly warmer air, so it's very difficult to get any upward or downward movement in the stratosphere, and weather doesn't happen there. That means that things don't rain out, so once something gets into the stratosphere, it can be very hard to get it out. If you've ever wondered why large thunderstorms have a sort of anvil shape, it's because they rise all the way up to the stratosphere where they get capped, and the air spreads out at the top since it can't get any higher. Okay, so that gives you a sense of the structure of the atmosphere to help you think about what's going on where. Let's get back to factors that directly impact climate change. First, here's a figure showing what actually happens to long-wave radiation that leaves the surface. It doesn't get absorbed uniformly. There are some regions where water vapor absorbs a lot of the radiation, and others where carbon dioxide does, and still others where much of the energy doesn't get absorbed at all on a clear day. So it's not totally fair to talk about shortwave and longwave radiation as if they're just two separate but uniform things. The atmospheric window, for example, complicates our model because some wavelengths of outgoing radiation are unlikely to get absorbed at all. If you look at the water absorption regions, you can see why it's the most important greenhouse gas from the perspective of total surface warming. Why do we focus on CO2 if water is a more significant greenhouse gas? Well, we generally think of water as something that follows other temperature drivers. If the temperature goes up, then that leads to more evaporation and thus more water vapor, and that increases temperatures even more. Scientists think that this positive feedback makes the current atmosphere about twice as sensitive to changes in CO2 as it would be without the feedback. Clouds also complicate our picture in a way that's very difficult to quantify because clouds do two opposing things. They absorb outgoing long-wave radiation even better than greenhouse gases, and that acts to warm the planet. On the other hand, they reflect away incoming short-wave radiation, and that acts to cool the planet. Moreover, some clouds, like puffy cumulus clouds, they reflect away a lot of shortwave, while others, like thin stratospheric clouds that often appear only as little rings around the moon, for example, they reflect almost no shortwave but still absorb a lot of longwave. And it's not just what kind of clouds form that affects whether they're likely to warm or cool the planet, but where and when also matters. So, for example, polar clouds tend to warm the planet, while tropical clouds tend to cool it. Nighttime clouds warm the planet, daytime clouds cool it. Winter clouds warm the planet, and so on. As the planet warms and more water evaporates into the atmosphere, that should also increase cloudiness on average, but we don't really know whether that's going to enhance the positive feedback from water vapor or diminish it. Recent work has suggested that it'll add to the warming, but that's not at all clear currently. A more complete picture of heat balance in the real atmosphere looks something like this, with units in terms of watts per square meter. You get about 340 at the top of the atmosphere. That's 1360 divided by 4. Of that, about 30% is reflected away, most by clouds, but some by the surface. A little less than a quarter gets absorbed by the atmosphere, much of that in the stratosphere, leaving about 161 to be absorbed by the surface. Some of the surface heat is lost to the atmosphere not through radiation, but through evaporation or direct heat transfer to the air through contact. More importantly, the Earth is about 16 degrees Celsius, so it radiates about 400 watts per square meter upward. Remember, you can check the math there. A little of that gets out through the atmospheric window, but most gets absorbed, warming the atmosphere, which winds up radiating about 239 watts per square meter into space. It also radiates back toward the surface. Because the atmosphere has the equivalent of many different layers, what goes out the top is not necessarily the same as what the Earth experiences. The surface experiences 342 watts per square meter of radiation from the atmosphere. Notice that the 239 radiated to space plus 100 that's reflected more or less equals what's coming in. Notice also that there's an imbalance of about half a watt per square meter, which causes warming. This net imbalance is different numerically from the atmospheric forcing that we'll talk about later in the course, but it is what is currently remaining in the system to create climate change.